Hi, in this video I'm going to talk about the dynamic programming. Honestly, I don't know what it's to do with the dynamic or programming. I don't know where the name comes from, but it's a approach for solving problems based on two things. The first one is recursion, and which means you try to somehow solve a problem according to the result from smaller set of problems. And the other one is memorization. Memorization means when you compute a value for a given number, you store it somewhere, so the second time that you need it, you don't compute it again. You just store it in a vector or matrix or something like that. So yeah, recursion will that means you somehow relate f of x to f of, I don't know, x minus 1, let's say f of 1x2, and so on. So when you want to compute, for instance, the f of x, which is based on a f of x1 and f of x2, you put here f of x minus 1, so here going to be f of x minus 2, and here f of x minus 3. So when you compute f of x minus 2, and you and your function called in pop back, when you come back here, you want to compute f of x minus 2, you have already computed, so you store it in a matrix, in a vector, or whatever. So the second time you don't compute it again, you just read it from the that's a concept of memorization and recursion. You can see it. So examples that I'm gonna solve, I get them from the Competitive Programmer's Handbook by Antti Laaksonen or something like that. It's free, it's available on his website, and I recommend you to read this book. It's a good book. Okay, the first problem I'm gonna solve by using dynamic programming is called coin problem. In this problem, I have a set of coins, and the values are 1, 3, and 4. And I would like to sum up using this coin, sum up the specific number, and I'm interested to use the minimum number of coins. For instance, f of 0 is 0. Well, if I don't need any money, I don't need any of these coins. If I need 1, I only use 1. If I need 2, I use 2 coins of value 1. If I need 3, I use 1 value of 1. If I need 4, I need I get 1 coin of value 4. If I need 5, I will get 1 value of 4 plus 1 coin of value 1. 6, 2 value of 3, and so on. So as you can see, you can somehow see the recursion part, that how I'm try to solve a problem according to the previous result. So for instance, if I need the f of 10, I can look at the previous answers, like f of 9, f of 7, and f of 6, and say, okay, the number of coins that I need is one of these solution plus 1, because I either grab one of these solution and I will add another coin to that. So I have to find the minimum of 9, 7, and 6, and I will just add 1 coin to that. Okay, and you can see here I did I get the minimum number from 2 times 4 plus 2 times 1. Okay, and sorry, I need 4 coins here. Okay, so if I want to write the recursion part, you can see f of x gonna be minimum of f of x minus 1, f of x minus 3, and f of x minus 4 plus 1. Okay, so I have to compute the minimum of one of these, and then at most I need to add 1 coin to that. So this is the recursion part, and for the memorization part, as you can see, I'm computing f of x minus 1, 3, and 4. So whenever I'm computing f of x minus, for instance, 4, I will store it somewhere. And when I'm going to f of x minus 3, which I have to compute f of x minus 4 again, I will read it from there. So I will just store them in a vector, and I will just read it from there. So the code for this problem is available on my website. I will put the link in the description, and there's a C++ code for that. And you can just have a look on the code to see how easily you can implement this recursion part and the memorization part. Okay, the second problem that I would like to solve here is called path in a grid. This is a very important problem, and you will see it in many applications. For instance, in dynamic time warping, and sim carving, for instance, in problem of scan line in the stereo vision. You will see this problem. Well, they have a slight differences. Like in some of them you have to maximize something, in some of them you have to minimize, some of them you start from here, some of them you start from there, but the basics is the same. They have some slight changes. So okay, let's first say what is the problem. You are from here, this is your start state, and this is your goal state, and you are interested to go from here to here. You are only allowed go either to the right or down. You are not allowed to go to the left. The numbers that you can see here is the cost of traveling to that cell. For instance, if I'm here and I want to go here, so that the travel cost is 8. Okay, so these are the assumptions: limitation and move, start and goal, and you can see the cost of each cell. So we are interested to have the maximum cost for going from start to the goal. You can see problem in dynamic time warping. For instance, let me just tell you in brief what are these problems. In dynamic time warping, you have basically 2 signals that are very similar, but one of them is stretch version of the other one. They are not exactly the same. There might be some noise on them, but you can see that this point, for instance, is this point is this point, and these points are this point. It's just been stretched, and there might be some noise on that. So you are not allowed to assign this point, I don't know, to that point. You cannot go back. So that's why you have some limitation in moving. You're only allowed to go right down. This has many applications. For instance, in and audio and speech processing. As I said, this might be to signal from when you pronounce a word, but in different time and duration. But they are the same. There's also, I have done a code for dynamic time warping in my website. You can also have a look. There's code in C++ and Python. SIM carving. SIM carving is another problem that you could use dynamic programming. For instance, you have a image like this. It's a scene, and you want to resize it. You want to resize it like this or like this. So you have to throw away some rows or columns, and the question is, which rows or which column should I drop? Well, let's say here you have a blue sky, and here you have a, I don't know, moon or sun, and here you have, I don't know, a bird, something like this. You have some edges, and here you have some edges here. Okay, if you want to throw away some lines like this, some columns, as you can see, the best place to throw away some columns are some places like here, because there's nothing interesting here. It's just a plain blue sky, or it's there's nothing important here. Basically, there is no edges there. Okay, you can see I have a lot of edges here. If I apply some first or second derivative, I could get a lot of edges. So if I store the value of the magnitude of these edges in a matrix, and I look for a path from bottom to down, which has the minimum cost in the terms of magnitude of the edges, then I can throw away that line, that column, or that rows. So this is a problem with SIM carving. You can use dynamic programming or finding the scan line in stereo vision when you have a right and left image, and you select a point here, and you're searching for the correspondence of this point in the second one, and instead of searching for one point, we can scan a line and search for a place of a line. So these are some application of path and a grid. As I said, they are slightly different. Sometimes you have to maximize, sometimes you have to minimize. Sometimes there are some limitation in a move. But these problems all have the same essence. Okay, enough talk. How to solve this problem? Okay, let's imagine I'm here. Okay, I'm already goal. If I knew, I could either come from here or here. If I knew the cost for this part, for coming to this part, I only add 8 to that, and then I have the cost for being in the goal. So I only need to compute the cost of this part or this part, because I could only come from here or here. So if I have the cost for this part or this part, I only add 8 to that, and then I know what is the cost. So I only have to find a minimum of moving from here to here and here to here. Okay, so we can see the recursion part, how I can write the recursion part. So the recursion part is going to be f of x and y going to be maximum of f of y and x minus 1, or f of y minus 1 and x plus r, y, and x. Okay? So this is r of y and x, cost of this particular cell. Okay, so that was the recursion part, and for the memorization part, you have to every time you have to store everything in a grid in a matrix, and every time you need to compute this part or this part, you have to have a look in the respective index on that matrix. If you have already computed, just use the value, otherwise compute it. Okay, so if I want to populate this matrix, I can do it for the first part. For instance, the cost of being here, which is 3. I'm already here. The cost of being here, I can only come from right, which is not possible, or top, like this. So I have a down part. So the cost is 9, and the cost from the previous part was 3. So it's gonna be 12. 12 plus 1, it's gonna be 13. 13 plus 3 gonna be 16. And 16 plus 6 gonna be 22. It's the same here. 7 and 3, 10. 10 and 9, 19. 21. And 28. Okay. Now, let's say you here. The cost you could only come from either here or here. So I picked a maximum value, which is 12, and I know the cost of being here is 8, so 12 plus 8 gonna be 20. So I just did this. Took the maximum from this guy and this guy, which was this and this, plus this guy, 8. I just have to write down something maybe to make it a bit more clear. So the indexes are like this. This is 1, 1. This is y1. This is 1x. And this is y and x. So y is the first element and the x is the second element. Okay. With some changes, you could apply it for dynamic time warping and scanline, stereo vision, or sim carving. And the code for these algorithms also available on my website. You can just go to the description and download the code. Okay, the third problem that you could use dynamic programming to solve the problem is called Levenshtein edit distance. This problem, the problem is finding the minimum number of changes that you need to one string to another one. For instance, movie and love. Imagine these two strings. If you throw away I and replace M by L, you can change movie to love. So you need only 2 changes. Okay, so the operation that you could do on 2 strings are 3 operations. Either you can insert, delete, or change. Okay, so you're allowed to do 3 operations: insert, delete, and change, to change one string to another one. And you're interested to the minimum number of changes. Okay, so if I want to compare one string to another one, I will look at the these 2 strings, and I would say, okay, if the last character is the same, I don't need to do any changes. The cost is 0. If it's not the same, I could go one step back and throw away one character from one string and compare it to the other one to see if I need to do an insert or not. Or I could throw away one string from another character and see if I need to do delete actually. So you can see the recursion part, how I'm gonna form the recursion part. So f of a and b gonna be a minimum of f of a b minus 1 plus 1. So here's a cause for delete f of a minus 1 and b. This is a cause for insert, and f of a minus 1 and b minus 1 plus c, which c could be 0 or 1. What does it mean? It means if I'm threw away one character from both, and basically they are the same afterwards, it means the last character was the same. So the cost of change is 0. Either this is the case, or I need to change one character. So I have to turn one, like changing the M to the L. Okay, so it at most gonna be 0 or 1. Okay, so insert, delete, and change, which is gonna be 0 or 1. So let's see how we gonna populate this table. So we start from here, and we say, okay, the cost of being here again is the minimum cost of being here or here. So I have to pop back until I arrive at here. So the cost of comparing a null string with a null string is 0. Okay. The cost of comparing null string with M is 1. I only need to do one change. So these are the insert part. Null with 2 string, MO is 2, null and 3, 4, and 5. And again here, the null string, which is a substring of a movie, with L is 1, 2, 3, and 4. Okay. Now the cost of comparing M and L, okay, is 1. We need to do one change. Okay. Now if I have LO and I wanna compare it with let's see, from here I will get to here. Okay, so now this is a case that this part is going to happening. So imagine you here, you start popping, you started from here and you pop back. You need to know the answer for this part. This part you might come from here, here, or here. So imagine now you're here. Okay, so it's MO and LO. So as you can see, we only need one change. So I could either come from here, here, or here. So I have to take the minimum cost for these changes, which is 1. Okay, sorry, I have to still fill out this part. So okay, to get the value for this part, I need the value for coming from here, which is basically substitution, or delete, or insert. Okay, so I need to know the answer of this part and this part. Okay, comparing LO and M, I need 2 changes, and M and LOV 3 and 4. Okay, comparing L and MO, you can see it's 2, L and MOV. I need 2 and 4 and 5. Sorry, it's going to be 3. Okay, so comparing the value minimum of 2, 2, and 1 is 1, plus the cost of C, which is the changes, which is 0 in this case, because both of them leads to O. So it's going to be 1. And basically you continue like that until you reach here. Again, I have done this code in C++. You can have a look on my website, and it gives you better intuition. Maybe it looks a bit confusing, but if you just debug the code and trace back, you can easily get the notion by having a look at this formula, and keep in mind the 0 and 1 and the first row and the first column, which you should put a special case for populating the grid. Okay, that was 3 examples for dynamic programming, and thank you for your attention.